So this video is all about your first introduction to something we call component form. It's another way to express a vector instead of drawing it, writing it in terms of its vector components. So this video is going to kind of show you what that means and then how to do it. So component form, like I said, is a way of expressing a vector as the sum of its vector components. So you've already had an introduction of what a vector component is. It describes the projection of a vector in a particular direction. And so now we're going to actually find these vector components for a particular coordinate system. We're always working in the Cartesian coordinate system. We're going to find each of these vector components and we're going to add them all together, and that's how we're expressing our vector in component form. So this is the graphical representation. This is what you've already seen many, many times, drawing the vector as an arrow, describing its norm as the length of this vector, and then its direction relative maybe to like a reference line, like this vertical line here. Another way of doing it is something called component form. So here's my vector A, and I've expressed it as a sum of vector components along the directions of my Cartesian coordinate system. So I have to show you my coordinate system for this expression to make any sense. And so that right there, that's our vector component of vector A in the x direction. So notice it's going to be some number times x hat. That's how I know that this is the vector component in the x direction. And now I have this one right over here. That one is the vector component of A in the y direction. And A is written as the sum of these vector components. So that's what we mean by component form. And again, this is all in the context of the Cartesian coordinate system. So when you see these x hats and y hats and z hats, if we're working in 3 dimensions, that this is the Cartesian coordinate system. And these unit vectors are mutually perpendicular. So x hat is perpendicular to y hat and z hat and vice versa. So this is how you want to do it. This is how to express a vector in component form in this Cartesian coordinate system. First, identify your vector. You need some kind of information about the norm of the vector and how it's pointing. So you might have this as a picture, or you might, like in words, it might have been given to you, but you need this information. Then you want to choose a coordinate system. We're always working in the Cartesian coordinate system, but you have the choice of how you want those unit vectors to point. Remember, as long as they obey the right-hand rule, then they are a valid Cartesian coordinate system. So x hat doesn't always have to point to the right, y hat doesn't always have to point up, and z hat doesn't always have to point out of the board. You get to choose these things, but you need to choose it and then write it down so that it's like you can reference that to describe this vector. And I advise you to draw these unit vectors tail to tail with any vector that you plan on putting into component form using this coordinate system. By doing that, it'll make step 3 easier. You need to identify the angles that the vector makes with each of the unit vectors when they're drawn tail to tail. So just draw them tail to tail every time. And then identify the angle that this vector makes with the x hat unit vector. Identify the angle that this vector makes with the y hat unit vector. And identify the angle that the vector makes with the z hat unit vector. Once you have all this information assembled, now you're going to plug it in to this expression here that I call the generic expression for a vector in component form in the Cartesian coordinate system. So it's written as the sum of scalar components multiplied by unit vectors, which means that it's the sum of vector components in each, along the directions of each of the unit vectors that define this coordinate system. All right, so we'll go a little bit, we'll do some examples here to show you, but these are the steps. Please reference these steps every time you're told to put a vector into component form. Use these steps as a reference to try to find all of these pieces of information and plug into this expression here. To go a little bit more in depth, I'm going to recopy this expression here. I just want to help you identify what this expression means. It looks kind of weird, it might be off-putting at first, but it really isn't that scary here. So remember that when you dot a vector with a unit vector that describes a particular direction, what you're doing is finding a scalar component of that vector along that particular direction. So you'll notice that each of these terms in the parentheses, and now that I've highlighted in these pink circles, these are the scalar components of vector A in each of the dimensions defined by our unit vectors x hat, y hat, and z hat. Remember, to construct a vector component, you take these scalar components and you just multiply them by the unit vector of that direction of interest. So down here you can see that vector A is written as the sum of its vector components along the unit vectors describing the Cartesian coordinate system. So you have your vector component in the x direction, your vector component in the y direction, and your vector component in the z direction. And this is what we mean when we say component form of a vector. I might not explicitly say Cartesian coordinate system, but that's all I've taught you. So you must be using a Cartesian coordinate system. You might be able to choose how the unit vectors point, but they have to obey the right-hand rule. So again, this is this expression, I kind of refer to it as the first generic expression for the component form of a vector in a Cartesian coordinate system. This is your go-to expression when you want to try to put a vector into component form. Now you guys know a lot about dot products. Notice that each of these scalar components is just written in terms of the dot product. So what I could do is I could replace that dot product using the definition of the dot product. So a dot x, this term right here, I could rewrite that as the norm of the first vector times the norm of the second vector times the cosine of the angle between them. So notice here in each of these terms, I've defined some angle that describes the angle between my vector A and each of the Cartesian unit vectors. So this angle alpha, that is defined as the smallest angle between vector A and x hat, and all of this is when they're placed tail to tail. So that's just kind of implied, but I'll write it explicitly here because I didn't type it out for you. So each of these angles describes the angle between vector A and a particular unit vector from the Cartesian coordinate system. So these are specific ones. When I say find alpha, I'm referring to the angle between vector A and x hat. If I say beta, then I'm describing the angle between A and y hat. Gamma, that's the angle between your vector and z hat. So get in the habit of defining these angles every time. We give them specific names because they're describing specific angles between whatever vector you're putting in component form and each of the Cartesian unit vectors. So this expression down here is just kind of the simplified version of everything. Instead of writing the norm of unit vectors x hat, y hat, and z hat, we know that the norm of every unit vector is just the number 1. So when you see the norm of each of these unit vectors, you can just replace that with the number 1. And so that's how I got this simplified version. That it's just the norm of A cosine alpha times x hat. So this is now, you can see that this is again the vector component. So it's the scalar component times the unit vector plus the norm of A times cosine beta y hat. So here's another vector component. And then norm of A cosine gamma z hat. Here's the vector component in the z direction. So again, this is just another way of expressing the exact same information, just in terms of the norm of your vector A and the angles that it makes when placed tail to tail with each of the unit vectors. So you might use this expression a little bit more often when you're trying to put the vectors into component form. It kind of takes some of these steps out of it, but this is where it comes from. It is exactly the same information as that first expression. It's just simplified a little bit. So let's do an example. I have a vector r here that I've tried to draw on. It's a three-dimensional vector, so it's pointing to the left, up, and out of the board. And I've defined the angles between vector r and each of these Cartesian unit vectors. Notice that in this chosen coordinate system, x hat is pointing out of the board, y hat is pointing to the left, z hat is pointing up. Do your right-hand rule and prove to yourself that that's a valid Cartesian coordinate system. Then I have some information here. Vector r has a norm of 12 meters, and in this particular coordinate system, r makes an angle of 75 degrees with x hat, r makes an angle of 135 degrees with y hat, and r makes an angle of 35 degrees with z hat. So let's express r in component form in this coordinate system. So I copied down the generic expression of a vector already for you. Now let's keep on going. So let's plug in some information here. So this would really be, I'm going to simplify each of these terms and using the definition of the dot product. So r dot x hat would be the norm of r times the norm of x hat times the cosine of the angle between them, which I call alpha. And all of that is multiplied by x hat. Plus norm of r times the norm of y hat times the cosine of the angle beta. That's the angle between r and y hat. All of that gets multiplied by y hat. And now vector r times the norm of z hat times the cosine of this angle gamma, and all of that is multiplied by z hat. So I've just kind of simplified these dot products using the definition of the dot product. Now we can plug in some numbers at this point. The norm of r is 12 meters. The norm of x hat is the number 1. And angle alpha, they told us, was 75 degrees. That was the angle between r and x hat. And then don't forget your x hat. That was kind of on the end there that defines this vector dimension, or this vector component. It needs a vector on there, so don't forget your x hats. Then keep on going. Norm of r times the norm of unit vector y hat times the cosine of the angle beta, 135 degrees, plus norm of r times the norm of z hat times the cosine of angle gamma, which they tell us is 35 degrees, and then times z hat. So I'm just showing it step by step, and now I'm going to actually calculate some numbers here. 12 times the cosine of 75 gives us 3.11 meters x hat, plus 12 times the cosine of 135 gives me negative 8.49 meters y hat, plus 12 times the cosine of 35 is 9.83 meters z hat. And here's my final answer. This is vector r, as simplified as it can be, written in component form. So it has each of these vector dimension or vector components added together. All right. So that's what you got to do. Sometimes it's easy and it's given to you like this, where they just tell you the angles between vector r and each of these unit vectors. Most of the time, you're going to have to figure those out. That's why we've done so much practice with finding angles to describe the angle between two vectors. So you've done a lot of practice on this. That we did it for a reason. It's because you're going to have to do it all the time in order to put a vector into component form. I have a couple more simple examples just to do a little bit more work here. So let's figure out what is the scalar component of vector h in the y direction. So I've given you vector h in component form. So this is component form already. It's already been done for you. And we want to figure out the scalar component of this vector in the y direction. Light bulbs in your head should be going off whenever I'm trying to find a scalar component of a vector in a particular direction. That means that I need to dot that vector with the unit vector that describes that direction. So all I want to do here is find the dot product between vector h and y hat. So I'm going to distribute this dot product, and so I'll get 3 terms that each of them has a dot product in there. So I get 6 x hat dot y hat minus 9 y hat dot y hat plus 10 z hat dot y hat. Now I'm going to use the definition of the dot product to keep on going. So this is 6 times the norm of unit vector x hat times the norm of unit vector y hat times the cosine of the angle between them. The angle between x hat and y hat is 90. All right, keep on going. So now I have minus 9 times the norm of unit vector y hat times the norm of unit vector y hat times the cosine of the angle between y hat and y hat. That's a vector in itself, so it's automatically parallel to itself, which means that the angle between itself and itself is 0. The last term, I have 10 z hat dot y hat, so that'll be the norm of z hat times the norm of y hat times the cosine of the angle between them. Again, these are Cartesian unit vectors. Z hat is mutually perpendicular to y hat, so that means the angle between them is 90 degrees. So now you can kind of plug in some more information. We know that every unit vector has a norm of 1, so each of these is a 1. Cosine of 90 is 0. Norms of my unit vectors, cosine of 0 is the number 1. And so to kind of simplify and put that all together, my final expression here is just minus 9. This is the answer. This is the scalar component of h in the y direction. And now when you look at that component form, doesn't that make sense when you after you kind of know how these component forms were built? They were built by finding scalar components and multiplying them by the unit vectors in each direction. So you could probably just look at that component form, and because you know you're working in a Cartesian coordinate system, you could probably just identify that just by looking at it. But this is the math that proves why the scalar component is just equal to that exact coefficient that you see right there in the component form. It's just all goes back to dot products. The last part of this question here, what is the vector component of h in the y direction? So vector components are built by multiplying the scalar component by the unit vector that describes that direction. So we just did all the work to find that scalar component, so that's -9, and now we just multiply it by the unit vector. So my final answer for this vector component of h in the y direction is just -9 y hat. That is that exact term right up there in the component form of vector h, because that's what component form is. It's the sum of the vector components along the directions of your coordinate system all added together. That's what component form means. All right, so this is the type of work. This is if you wanted to show all of your work to get those things. This is what I'm looking for. I want to see that you understand how to do a dot product, and you understand how the unit vectors are mutually perpendicular, and that's how you get these answers, other than just like looking at this component form. It's just kind of reinforcing what this means.